All right, students, here we go. Last chapter. All right, looking at fluids and fluid density. Now, some of this will probably going to sound familiar to you, and some of it may be new, so just bear with us. All right, now, of course, hopefully you understand what a fluid is. Anything that will flow is considered to be a fluid, okay? Typically, we consider fluids to be liquids and gases only. However, solids can also flow. When we look at glass, glass is not a true solid. Glass will actually flow. Has a very slow flow rate, but it will flow nonetheless. That's why if you go in a really old building, you will see, and especially if it's 400 or 500 years old and it still has some of the original glass in it, the panes will rattle. And typically they don't let it go that long because they'll eventually fall out, and so they have to regrout the glass. Okay, you see that a lot in buildings in Europe, some of those really old buildings. All right, so anything that will flow, mostly, for the most part, liquids and gases. Now, mass density is, of course, simply put, the ratio an object's mass to its volume. Rho, the Greek letter rho, is how we write it. Sometimes you may see it written this way. I don't really like to write it that way because D many times means distance in physics. So we use the Greek letter rho. You can remember this equation this way, and some of you have probably seen this. You can take a triangle and do this right here and say rho, m, and v. And if you're solving for the density, you cover up the rho, and it's mass divided by volume. If you solve for volume, you cover up the v, and it's mass divided by density. If you're solving for mass, cover up the m, and it's side by side, density times volume. So that's a good way to remember it. Now, the SI units of mass density are kilograms per meters cubed. However, we do use this right here a lot, grams per centimeters cubed. So many times on various tables where you see the densities listed, many times you may see it listed grams per centimeters cubed or grams per milliliter. You will see it written that way. And you might even see it written in kilograms per liter. We could write it that way, kilograms per liter. But the SI is kilograms per meters cubed, okay? And here they give you an idea of, or gives you an example of some densities that talk about gasoline. And of course that means that there's 680 kilograms of gasoline for every cubic meter of liquid gasoline. Water has a density of 1,000 kilograms per cubic meter. Now you can see why gas will float on top of water. It's about half the density of water. Okay, here are some common densities in kilograms per meters cubed. Air at 20 degrees Celsius. Notice it's a little more dense at 0. Gasoline, ethyl alcohol, oil, water, there's 1,000 kilograms per meters cubed. Seawater is a little more dense. Blood, a little more dense than that. Glycerin, and then mercury. Wow, look at mercury. I've seen video demonstrations where they'll take a cannonball and float it in a tub of mercury. Okay, it will actually sit on top of the mercury. That's crazy. Well, it's because it's a lot more dense than iron. Okay, so here's an example. What is the mass of air in a living room with the dimensions 4 by 6 by 2.5? So we first of all have to find the volume. So we multiply 4 times 6 times 2.5. And we get 60 meters cubed. And we look at the table we just had. Air at 20 degrees Celsius has a density of 1.2 kilograms per meters cubed. We multiply it times our volume, and we get 72 kilograms. That's kind of hard to believe. I know some people think, you mean to tell me that the air has that mass, 72 kilograms? That's a pretty good bit, isn't it? And you say, well, why do we not feel it? Well, we do feel it. It's called air pressure, okay? The thing about that is you got to realize is that mass is spread out over the entire room, not on one particular point, okay? And that's why. Now, so let's go ahead and look at pressure. Pressure is defined as in objects the amount of force applied to the area of an object. And so regardless of whether it is a solid or a liquid or a gas, and yes, you can put pressure on solids, of course, and it's calculated the same way, but we look at the pressure, and notice that's lowercase p, so force is in newtons and area is in meters squared, and so the unit for that, I'm probably getting a little ahead of myself, is the Pascal, okay? 1 Pascal, 1 PA, okay, is equal to 1 Newton per meter squared, okay? So in other words, if you apply 1 Newton force on an area of 1 meter squared, you have 1 Pascal of pressure, and that is the SI unit. And yes, you need to write these equations down. I hope you're already writing them down, okay? And you need to remember these units and what they're made of, okay? All right, so you want to write that on your formula card. There's your basic pressure equation. Now, what about pressure in liquids? Well, remember now, from our pressure equation, how do we find this? So the force of gravity, of course, is always acting on all objects on the surface of the earth and in the atmosphere. So it's applying pressure, and you also have atmospheric pressure. So how would we find the vertical forces that balance? Well, notice that pressure times area is force, okay? And pressure times area is force, and mass times G is force, okay? So in a sense, we could say the net force would be equal to what? The sum of those two forces, right? And so we could find the actual, the net force on any particular object if we know the its original force based on the original atmospheric pressure in the area, and then of course the force of gravity acting on it. So based on that then, we can find the pressure at any particular depth based on what? Well, the final pressure, or we might could say the net pressure. So final pressure or net pressure of a liquid at any particular depth is going to be based on the initial pressure, which typically that is atmospheric pressure, okay? Typically when we talk about initial pressure, that is the atmospheric pressure pushing down on the liquid. Then we have to take into consideration the density of the liquid times the acceleration of gravity, and then how deep is the object in the liquid, okay? And so we can find then the net pressure, or just pressure of a liquid with a particular density at a particular depth. All right, now, so if we assume that the fluid is at rest, then this pressure is considered to be a hydrostatic pressure, okay? It's not moving, it's just sitting there in the liquid, okay? Just like that diagram there, okay? So there's another equation for your formula card. Now, pressure in liquids. Now, this is really unique. If you take two containers, two columns, and you connect them, and notice it says a connected liquid in hydrostatic equilibrium rises to the same height in all open regions. So in other words, what do they mean by that? Okay, they say, look, if you take two different shaped containers and you put the liquid in them and they're all connected, they should rise to the same height, okay? So in hydrostatic equilibrium, the pressure is the same at all points on a horizontal line through the connected line liquid of a single kind, okay? So in other words, the pressure here and the pressure here is the same. The pressure across here is the same. The pressure across there is the same, okay? So basically, that is someone's law, and we'll get to in a second. So the iceberg floats in shallow sea. What must you say about the pressures at points 1 and 2? They are the same because they're in hydrostatic equilibrium, okay? What about here, 1 and 2? Well, guess what? They are the same because they are at hydrostatic pressure, hydrostatic equilibrium. And that leads to Pascal's principle. If the pressure at one point in an incompressible fluid is changed, the pressure at every other point in the fluid changes by the same amount. Okay? So, in other words, what do they mean by incompressible? If you take, like, for example, hydraulic oil, and you put it in two pistons and you seal those pistons, guess what happens? As you begin to move the piston, let's go back to our diagram. Well, let me just do this. Okay, so as you take a column, let's say like this right here. I didn't mean to close that. All right. Okay, so we go over here. Come in here. Okay, and we seal this off and put a piston in here. And then we got another little piston here like this. Okay, and you begin to push down on this piston. You apply force to this piston. Okay, then guess what? An equal force is applied to that piston. Now notice this piston is much, much larger. So if you recall from our equation that pressure is equal to the force per unit area, then guess what? The pressure at one point is the same. It goes unchanged. However, since the area of this piston is much greater, we actually multiply our force. Okay, even though the pressure is the same, you can take a very low force and raise something that is very massive. Okay, does that ring a bell with anybody? Hydraulics. Hydraulics works this way, okay? A hydraulic jack works on this principle, works on Pascal's principle, okay? And these are very useful. I mean, we use them in auto body shops and auto technology shops. They use them in, oh heavens, and everything. Hydraulics is used in so many different things. It's very useful application of Pascal's principle. Now, atmospheric pressure, it's amazing that 99% of our atmosphere is below 30 kilometers. So about 30 kilometers, that's going to be, let's see, 1 mile is 0.621, 1 kilometer is 0.621 miles. So that's about what? About 16, 17 miles. So about, when you go up to about, surface up to about 17 miles, you're basically passing through all of the atmosphere. Okay, 90% of atmospheric mass is actually found within the troposphere, which is the first layer of the atmosphere. And yes, gases are compressible, so air is something that can be compressed, all right? Hence, we have high pressure and we have low pressure systems, all right? Now, hydrostatics. Now, just some basic things to remember when you're measuring and using pressure. Of course, you want to draw a picture. You want to determine the pressure at the surfaces. That's P initial, or P naught, as we say in physics. The closed surface, then look, it's P naught is equal to the force divided by the area. And then, of course, if we want to know gauge pressure, then the pressure on the gauges would be what? The pressure minus 1 atmosphere, okay? And then hydrostatic pressure, here you go, okay? Okay, all right. So these are, it's a useful little table to remember, all right? Now, here we have a manometer which measures gas pressure. And of course, if we take this tube, the tube is filled with liquid. Many times this is mercury that we use. And mercury, why do we use mercury? Because mercury is very stable. It doesn't change as far, and I'm not saying chemically stable per se, but mercury expands very evenly, okay, through a wide range of temperature changes, okay? So it's a very reliable liquid, and provided you keep the temperature constant wherever it's used, or fairly constant, okay, you're not going to get a whole lot of change. In other words, it doesn't expand at a variable rate, okay? Whereas liquids, that's not always the case. Temperature greatly affects the volume of a liquid, okay? All right, now, okay, so here we say equating the two pressures gives us this, that the pressure of the gas, of course, is equal to 1 atmosphere times the density of the gas times acceleration of gravity. Notice we always have to take that into consideration, times the height of the column here, okay, from here to here, okay? And that's how we would find it, the pressure of a gas. Now, so if we're using a barometer, then how do we find atmospheric pressure, okay? Well, a barometer, basically what we're doing, and if you remember hydrostatic equilibrium, whatever the pressure is here, the pressure will be the same there. So how do we find atmospheric pressure? Well, Bernoulli, Torricelli, when he made the first barometer and basically discovered, or I say discovered, he he didn't necessarily discover air pressure, but he discovered the way to measure air pressure very accurately with very high precision by creating this device here. And it was very similar. It looked very similar to something like this. Using a glass column closed at one end, and it had mercury in it, and then he put it in a pool of mercury, and he walked up to the top of a hill, and he measured the column of mercury at the seashore, and then walked up the top of a hill. I think it was 200 or 300 meters high. And guess what? The column of mercury changed. And of course that shift in that change as the column moved, we measure that in, actually it was measured in millimeters of mercury. We still use that, or centimeters of mercury, and we still use, typically we use millimeters of mercury. But anyway, we find the pressure of a gas by knowing the density, okay, the density of the liquid times the acceleration of gravity times the height of the column. And again, that height of the column is from here to right there, okay? All right, so we can find atmospheric pressure that way. Here we see some pressure units. Again, it's always going to be in pascals for the SI unit anyway. I know some of you are familiar with inches and PSI. We're more familiar with that than we are pascals until we get into chemistry and physics. So 1 atmosphere of pressure, we write it that way. It is 101.3 kilopascals, or 101,300 pascals, okay? 1 atmosphere, we use that as a general term. They say, okay, how many atmospheres of pressure are we at? Well, we're at 1 atm. Well, what is 1 atm? Well, it's that in pascals, okay? We use 760 millimeters of mercury for barometers, again, going back to Torricelli. And that's a very good way to measure pressure. Then in the English system, we use 29.92 inches of mercury, and again, that's in the United States where we use that. And then, of course, 14.7 pounds per square inch in the United States and in industry. And they left another one off, too. We used in 1,013 millibars. And we use this in weather forecasting, okay? Weather forecasting. 1,013 millibars is 1 atmosphere of pressure. And of course, these are all of these are 1 atmosphere, okay? So they left that one out, and I thought I'd throw that, because sometimes you'll hear the meteorologists talk about hurricanes, and they'll say, well, it's down to 900 millibars. That is a very intense hurricane. I think the lowest ever recorded pressure in a hurricane was 888 or 887, somewhere right in there, millibars. And that wasn't too awful long ago. Well, maybe 15, 20 years ago. I think it's Hurricane Gilbert, I think. I don't know. Katrina may have actually broken that record. So double check me on that, okay? All right, let's look at buoyancy real quick. Buoyancy, of course, is the upward force of a liquid on an object. And the pressure in the liquid increases with depth, so the pressure in a liquid-filled cylinder is greater at the bottom than at the top. I mean, come on, y'all know duh, right? I mean, everybody ought to know why. Well, because you have atmospheric pressure pushing down, and then you have the density of the liquid times the, phooey, I hate it when that happens. Okay, let me move over. All right, so you've got atmospheric pressure pushing down, okay? And then you've got the density of the liquid times G times the height of the liquid, right? So you actually should have a lot higher pressure at the bottom than at the top. That's just common sense. So the force net is equal to what? And I like this diagram. The force up, which is this force, minus the force down, which is that force, okay? Now force down can actually be listed as mg, okay? All right, now, notice that the force net is equal to the buoyant force, okay? So we call that the buoyant force, all right? So buoyancy, if you have an isolated parcel of a fluid in static equilibrium, then the parcel's weight force pulling it down must be balanced by an upward force. That's called the buoyant force. Now, the buoyant force matches the fluid weight. Notice that right there. Notice it says fluid weight. Did not say object weight. It said fluid weight, okay? Very important, all right? So if we replace that with the same shape, size, with an object the same size as the buoyant force on the new object is exactly the same. So what are we getting at? as long as the size of the objects are the same, it does not matter how the mass of the object, okay? As long as the size or the volume of the objects are the same, then guess what? Then the buoyant force will be the same. Isn't that neat? So, when we have an object immersed in fluid to displace the fluid, otherwise that region, fill that region of space, the fluid is called the displaced fluid. No duh, right? So Archimedes' principle basically says what? That a fluid exerts an upward buoyant force on an object immersed in a floating, in or floating on a fluid, okay? So the magnitude of the buoyant force equals the weight of the fluid. Very important. The magnitude of the buoyant force equals the weight of the fluid displaced by the object, not the weight of the object, okay? The weight of the fluid, not the weight of the object. Please get that, okay? So the buoyant force then can be written this way, and you do need to write this equation down. The density of the fluid times the volume of the fluid times acceleration of gravity. That's G is acceleration of gravity, 9.8 meters per second squared, okay? So be sure I didn't mean to do that. Damn it. All right, so be sure you get that, okay? Very important. Now, let's move on. So if you have a heavy lead block and a light aluminum block of equal size, are both submerged in water, upon which is the buoyant force greater? Well, come on, y'all. They are of equal size, same volume, so they both experience the same buoyant force. Isn't that neat? So you can take a very massive object, has a very high mass, put it in water. Well, guess what? The water helps you. You not ever noticed how someone, and I'm a big guy. I don't know, some of you may know me, some of you don't. I'm 6'5", 310 pounds. Oh, Lord, too much. But anyway, we were at the beach last week, and my kids, we were in the pool, and they said, Papa, let me see if I can hold you up or, carry you around in the pool. And, of course, they can. They're a whole lot smaller than I am. My middle son, he's a pretty good-sized boy. He's 15, but still, I outweigh them a good bit, a lot, especially my youngest boy, and they could just pick me up and just walk around the pool with me in the water. Why? Because the water helps to, remember now, the amount of water I displace, the buoyant force, is based on how much water I displace, okay? So I'm displacing a lot of water because I'm a big guy, right? Okay. All right, the weight of the water displaced, not my actual weight, okay? So if you have two blocks of identical size, one is lead, and for some reason I accidentally deleted the first slide, sits on the bottom upon the other is of wood and floats on the top, upon which is the buoyant force greater. Well, have to be on the lead block, okay, because it's completely submerged, okay? It's completely submerged. All right, now, okay, so whether an object released underwater will head to the surface, the bottom of, depends on whether the upward buoyant force in the object is larger or smaller. I mean, come on, y'all. So how do we find that? We find that using something called the average density. And the average density is the initial mass divided by the initial volume. Okay? Now, the weight of a compound object can be written this way. This is a very useful equation. The weight of an object, the initial weight, can be found by the P average times the volume initially times the acceleration of gravity, okay? So you might want to write that down, the weight of a compound object, okay? All right, now, so when we put this in here and the object's floating, okay, if the densities are equal, then the object is in static equilibrium, it hangs motionless, all right? All right, so if we got an equal density, then guess what? That block is at what's called neutral buoyancy, okay? It's at neutral buoyancy. All right, now here's a good little diagram. Float or sink, finding whether an object floats or sinks. If an object, now look right here, if an object sinks if it weighs more than the fluid it displaces, okay? Now remember, you said, well, wait a minute, Mr. Shields, I thought you said the buoyant force is dependent on the weight of the fluid. Well, it is, okay? But it's the weight of the fluid that it displaces. And if the weight of the object is greater than the weight of the fluid that the object is displacing, then come on, y'all, it has to sink, okay? It has to sink. That's why when you punch a hole in a ship, when they would shoot torpedoes and put a hole in the ship under the waterline, guess what happens? Well, the ship starts to fill with water, and eventually the weight of the ship becomes greater than the weight of the water it's displacing, and it sinks, okay? That's how that works, all right? Now, so if an object rises, needless to say, its density, average density, or it weighs less, okay? It weighs less than the fluid it displaces, and if it floats, then they are equal, okay? And that's called neutral buoyancy, okay? So I did it again. Which floating block is most dense? Doggone it, it's that one, okay? And you say, how do you know? Well, look at how they are in the water. Notice this one's about 2/3 out of the water. This one's half out of the water. This one here is about 3/4 underwater, okay? So it has to be the most dense, okay? All right? Well, how do you know? Well, because it's about to sink, all right? Okay, all right, okay? Boats and balloons. The hull of a boat is really a hollow shell, no duh. But again, it all depends on how much water the boat will displace, and that has a lot to do, the weight of the water that is displaced by the boat, and that has a lot to do with the boat's weight, okay? And that's what I just said, okay? Notice it says the boat sinks until the weight of the displaced water exactly matches the boat's weight. All right, come on, that's what I just said. I just said that a minute ago, okay? So, you keep loading the boat up, guess what's going to happen? It's going to sink. Now, look here. We're about to maximum right here, all right? We're about to maximum. So, you know, you can't overload a boat, okay? Why do you think boats have, you know, maximum capacity on it or maximum weight capacity? You know, if you've got a weight capacity of, I don't know, 1,000 pounds and you put 2,000 pounds in it, it is going to sink, okay? I don't care what anybody says, it will sink. Now, same thing with a balloon. The density of the balloon, the gas in the balloon, has to be less than the density of the air. That's why they use heated air, because heated air is less dense, okay? It's much less dense. Or they use helium or hydrogen, a gas that has a lower density than air, okay? But heated air is less dense than cooler air, cold air. Why in the world do you think hot air rises, cold air sinks? Because hot air is less dense, okay? All right, doggone it, I did it again. Blocks A and B and C are all the same size. Which experience the largest buoyant force? Well, they are all the same because, look, they're floating, okay? Because they're all the same size, okay? Okay. Fluids in motion. Now, this gets interesting. All right, now, fluids in motion. Anytime we look at fluid dynamics, we use what we call a simplified model. We assume a few things here. First of all, the fluid is incompressible. So it's a good assumption, but it also holds reasonably well for moving gases such as air, okay? So, for instance, even when a 100-mile-an-hour wind slams into a wall, its density changes only by about 1%. How about that? So we can use that. The flow is steady, all right? That's another thing. So when we look at fluid velocity at each point in the fluid is constant. It does not fluctuate or change with time. The flow under these conditions are called laminar flow, okay? And is distinguished from turbulent flow, okay? So we have laminar flow and turbulent flow. And so if they're all, at all points in the fluid the velocity is the same, we have laminar flow. Laminar meaning layered, okay? It's laminated, okay? And then if the fluid is non-viscous, water flows much more easily than cold pancake syrup. Well, why? Because it is not as viscous, okay? And you have good laminar flow. All right, so notice here. We have rising smoke. What happens when it begins to rise? Notice it comes out as laminar, but then it transitions to a turbulent flow, okay? All right, and of course this is not uncommon, all right? All right, now, so we're only going to look at laminar flow. Now, the equation of continuity. This is really interesting. All right, when we compress a fluid, when we take a fluid, and notice how large this cylinder is right here. Notice how large the pipe is, but then we narrow its volume. We make the volume much smaller. We have a large volume, then it goes to a small volume. Well, what do you think is going to happen? Well, the velocity of the molecules will change with different cross-sectional areas of the tube, okay? So they talk about area or volume. Actually, we can look at it either way. So notice this. So the volume, the change in volume, well, excuse me, they're looking at changing volume and comparing it to area. Okay, so if you take the volume of 1 here and compare it to the volume of 2 here, well, then these are going to equal each other. But notice what happens here, that as we change the position, which is basically saying what? As the velocity of the fluid through a given time interval, because why are they using that? All right, y'all, look. Remember how we found velocity? It's delta x over delta t, so delta x is found by what? Velocity times the change in time, isn't it? So look, we can take that and plug that in right here for delta x, okay? So what are we saying then? Then the velocity in area 1 will change accordingly to the area 2, or the velocity of 2 will change accordingly to the change in area from 1 to 2. So what are we trying to say here? So if we take both equations divided by delta t, we get what's called the equation of continuity. And notice that the velocity of cylinder 1 or tube 1 should be equal times the area of 1 should be equal to the velocity of 2 times area 2, okay? All right, so please remember this equation as the equation of continuity. Now, when we take the volume of incompressible fluid and entering one part of the tube or pipe, it must be matched by an equal volume leaving downstream, okay? So in other words, the volumes have to match, okay? You cannot put 100 cubic meters in one end of the pipe and get out 10. Okay, that's just impossible. All right, so what has to happen then? Well, guess what? That means that the flow in the smaller area has to increase. Okay? So you say, well, if the volumes are equal but the area decreases, then how does that work? Well, we have to increase the velocity of flow. Okay? We have to really speed up that velocity, okay? All right, so the rate at which a fluid flows through a tube, what we call flow rate, is the volumes per second. And please remember that Q there. That's what we call flow rate. And the unit for flow rate, okay, here's the units. Well, I don't need to write it down because it's already written down for you. The units are meters cubed per second, okay? So another way to express this, the meaning of the equation continuity, is to say that the volume flow rate is constant at all points in the tube. So what does this mean? Now notice here that the water coming out of the spigot is the same. It's a continuous flow, all right? It's the same. All right, right here, whatever the flow rate is here, okay, it's the same here, all right? Whatever the flow rate is here is the same here. But now wait a minute. The flow rate here and the flow rate there, okay, the speed increases, okay? The speed increases. So that's why you put a nozzle on the end of a hose and it's coming out a whole lot faster, okay? All right, and it helps you to wash things and whatnot, all right? Now, streamline. Now this is very interesting. When we look at streamlined fluid elements, notice that the streamlines here going over the car in this wind tunnel, notice how they're far apart here, but they're real close together here. They're fairly close together here. They're really close together there, okay? Notice that, okay? Now, notice it shows you here where the speed is higher where the streamlines are close together. Got high speed here. Notice they never cross. All right? And of course here they're going to be slower because they're farther apart. So wherever they come close together, all right, wherever they come close together, you've got a high speed. Well, we call that area and these segments here called the fluid elements, and that's just to put, basically what is that? We're just saying, all right, we're taking a section of the fluid here, we're going to call that a fluid element, okay? All right. Okay, and notice how they remain constant, okay? You can keep, the shape can change, but the volume remains the same, okay? Has to, all right? Now, let's look at fluid dynamics. All right, so again, going back to what we were talking about flow rate. All right, we take a large pipe, reduce it down to a small pipe. The volume of water is going to remain the same. You know, whatever goes in's got to come out, but the velocity increases, okay? So it increases, and of course thus increasing pressure. Now, so we call this gradient, it's called a pressure gradient. And so you're actually doing what here? You have a low pressure side and a high pressure side, okay? You're going to have a lot greater pressure here than you are here, okay? Much greater pressure, and that's called a pressure gradient. Now, all right, so it accelerates whenever there's a pressure gradient. Well, it'd have to, y'all. If you have a change in pressure, then you're going to have acceleration, and acceleration gives it force, doesn't it? Sure does. So the pressure is higher at a point along the stream. The pressure is higher at a place along the stream line where the fluid is moving slower. So you got high pressure here. I think I just said that backwards, didn't I? Yeah, you got high pressure here and lower pressure over here. Okay? All right? Much lower. And so what happens is you actually create an area of low pressure, or you create like a vacuum. It causes suction. Now this process is called the Bernoulli effect. So anytime you have a fluid moving through a large tube, okay, where it's moving slower, you have high pressure. Where it's moving faster, you have low pressure. Much narrow opening. We also get into what's called the Venturi effect when we look at carburetors on lawnmowers and cars with the old carburetor systems. It worked on the same principle. Some of you may have wondered, how in the world does the gas get into that carburetor when the gas tank is down here? Okay, have you ever wondered how that works on a lawnmower? You ever wondered how that works? Now, years ago, carburetors were gravity feed, and those things were just not as reliable. Okay, I mean they were, but they were problematic sometimes. Okay, now these suction feed carburetors, notice you've got air coming in the mouth or the throat of the carburetor, then it narrows. If you ever look at a carburetor, you'll notice how it narrows, and you've got your little needle valve right here, except it's upside down. Your needle valve actually goes, well, no, it comes up in here. I'm trying to remember how it works. So you have your tank down here. You've got your tube going down in here to pull the gas up in there, and then you've got your little needles going down here, your little needle valve. Okay, it's got a screw on the top of it. And so what happens is the fuel is sucked out of the gas tank by this lower pressure, because there's an area of low pressure here, area of high pressure there. That's in a carburetor, it's called the Venturi effect. It's called the Venturi of the carburetor, okay? But it's basically based off the Bernoulli effect, all right? All right, same thing happens when you have air passing over a curved surface. You know, actually, hills and mountains causes air to the streamlines to buckle and warp and get close together, and so what happens, we get a higher airspeed, and higher airspeed causes low pressure. And so guess what? Air rises. This up here is high pressure, okay? And so you can get air to rise. Many times you see air forced up a mountain. Part of it has to do with the streamline effect and the creation of low pressure, but it also has to do with the lifted condensation level. So it's not all to do with the shape of the mountain. The condensation is also based on the moisture and the temperature of the air, the dew point of the air. So when it reaches a lifted condensation level, it's going to condense, okay? So how does an airplane take off? Well, you have a curved surface, okay? So this curved surface, and actually the bottom of an airplane wing is flat, okay? You have a curved surface on top, you create an area of low pressure, you create suction, you create a vacuum, V-A-C-C-U-M, is that right? Lord, I can't spell worth a flip, all right? College ruined my spelling, all right? Yeah, You get a vacuum. Of course, the bottom of an airplane wing is flat. You have high pressure. Okay. All right. And so, boom, sucks the plane off the ground. Okay. Same thing here with houses. When we design houses in hurricane-prone areas, we have to really, really make sure these rafters, they'll strap these rafters down. And even then, if the winds are extremely high, it'll still pull the roof off, okay? And same thing with tornadoes. Tornadoes, same thing. It'll pull off, all right? Okay. Now, this is a neat little demo you can do yourself. You can take a piece of paper and blow straight out over the top of it and watch the paper rise, okay? Oh, and by the way, that's another reason you don't ever get under a bridge overpass on the interstate if a tornado is coming. You know, you don't ever, you just don't do that, because if you get way, and I know some people say, well, I'm going to climb way up high and get up in there where it's real tight. That is a no-no, because when the wind hits that bridge, the Bernoulli effect kicks in, and the air increases in speed even more, and it will suck you out from under that bridge. Hurricane went through Oklahoma City, went right down, I think it was I-35 for about 4, 5, 6 miles. I think it was in 99. And it was coming right down the middle of the interstate, and so people saw it coming. They got out of their car and got up under a bridge overpass, and it killed every one of them. The tornado hit the bridge, and it pulled every one of them, sucked every one of them out from under that bridge. And I think it was about 15 or 20 people that killed them. And they found their cars scattered down the road, and they got to looking for them, and they weren't in their cars. They had been up under that bridge overpass. So you do not do that, okay? Lay flat in a ditch. If you can't make a right turn, if the tornado is moving, you're moving south. If you're going south and you look to your right and you see the tornado coming at you, then you need to make a left turn. Okay, you need to make a left 90-degree turn to get away from its path. Or better yet, get in the ditch. I mean, if you're real close, you just need to stop and get out and lay flat in the ditch. Okay. If you're moving north, then you would need, and it's on your left side, and then you would need to make a sharp right turn, or better yet, just get out and lay flat in the ditch. That's the best thing to do. You don't ever try to outrun a tornado in a car. You just don't do it. You're not going to win. Okay. You do not outrun a tornado in a car. That is the last thing to do, okay? All right, Bernoulli's equation, we see that there is a relationship. Of course, anytime, if we want to find the work, and we know this from the previous chapter when we talked about work, I think it's chapter 10 and 11, we know that the kinetic energy, 1/2 mv squared plus mgh, will equal the total work done by a fluid, okay? Now, so applying our equations here, if we take a particular fluid and we look at the kinetic energy of the fluid, notice how it's very similar to our our mechanical kinetic energy equation. It's 1/2 the density times the change in volume times the velocity. Look at there, velocity squared. That hasn't changed, has it? Okay. So we've got the density times the volume, and why do we do that? Well, because we've got to get that into kilograms, okay? All right, and so the kinetic energy of 1 should be equal to the kinetic energy of 2, and of course the same goes for potential energy, all right? And so the change in kinetic energy, anytime you see changes, delta K, it's changing, so K2 minus K1. Now, same goes for potential, all right? Same thing goes for potential. Except notice it's the density times the change in volume times the acceleration of gravity times the height of the fluid. Okay? So positive and negative work are done this way. Okay? Notice that the work done of 1 is, of course, the force times the change of position, which is the same as saying what? The pressure times the area times the change in position. Or we can write it this way, the pressure times the area times the change in position, which is equal to basically saying the pressure times the change in volume. Now, so the work done on 1, the work of 1 on 2 has to be negative, doesn't it? So 2 has to be negative. So notice we stick a negative sign in there, okay? All right, I hope that makes sense. Okay, and there's some more equations you can write on your formula card. So Bernoulli's equation, this is one I actually want you to write down. You don't have to do those others, but this is the one you need to write down. So when we take both of these equations, when we take kinetic energy and we take potential energy and we put them together, then Bernoulli's equation says that the initial pressure of 2 plus its kinetic energy plus its potential energy is equal to the initial pressure of 1 plus the kinetic energy of 1 plus the what? The potential energy of 1, okay? And so please write this down on your formula card for Bernoulli's equation, okay? All right. Notice how the volume canceled out there too. All right, viscosity and Poiseuille's equation. Viscosity is the measurement of a fluid's resistance to flow. So if it has a high viscosity, then it does not flow very well. If it has a very low viscosity, then it flows extremely well. We want the viscosity of our motor oil to be low. We want it to flow. In other words, we do not want it to have a high viscosity. Okay, we want it to, well, let me think about that. We want it to have a, we want it to be very sticky, yeah. We want it to resist flowing. We want it to stick, so we want it to have a high viscosity, okay? So I had to think about what I was saying there for a minute, because we want the motor oil to stick to the parts, don't we? I mean, we want it to flow, but when it flows, we want it to stick to the parts, right? Okay, now, so when we look at pressure and Poiseuille's equation, viscosity and Poiseuille's equation, notice that the pressure difference needed to keep a fluid moving is proportional to the average velocity, the tube length, and inversely proportional to the cross-sectional area. So Poiseuille's equation is equal to the change in pressure, now that's delta P, the change in pressure, is equal to 8 times pi times n, and n is the coefficient of viscosity, and the units are newtons, seconds per meter squared, or poise, PA, or Poiseuille seconds, okay? Poiseuille seconds. PA is a symbol for his unit, okay? All right, now, here's some common viscosities. Notice that the viscosity decreases with rapid temperature change. Remember we were talking about motor oil. You know, you want to keep it, you don't want the viscosity to break down when the temperature gets high. You want it to still be viscous and stick to the parts, right? So here we see the different ones. Notice motor oil, very viscous at -30, but at 40, it's 0.07. At 100, it's 0.01. Okay? All right. Okay? Poiseuille's equation, again, dealing with viscous fluids. Notice here is an ideal fluid. Notice they're all moving along at the same speed. The velocity is the same. However, that's really not always the case, because you got to realize something, that the fluid close to the chamber walls is going to be slowed down by the chamber walls, okay? And so this fluid being slower will react on this fluid, and so forth. So a lot of times your highest velocity will be in the center of the fluid, okay? If the material it's flowing through, in which most cases you don't get ideal fluid flow. You just don't, all right, because of friction. All right, so the average speed of a viscous fluid can be found with this equation. Again, that's going back to the pressure of Poiseuille's equation and solving for velocity. So look right here. The volume flow rate, and you do need to write this down, for a viscous fluid is what? Q is equal to the velocity average times the area, which is equal to the pi times the radius to the fourth power times the change in pressure divided by 8 times Poiseuille's constant times the length. Okay? All right, so you can solve it either way there. You can use this one, or if you have to, you can use that one. Okay? All right, so I hope you're writing these equations down. And that's it.